Here's the question that I ended the previous part of this video lecture with, and I'm going to go through these answers in a fair bit of detail because there are a lot of misconceptions that people have when they're drawing free body diagrams, and those misconceptions lead to other problems. So first of all, the elevator is accelerating up and the woman is accelerating with it, so her acceleration cannot be zero. You may have been thinking that if you were standing next to her in the elevator, her acceleration would be zero. But if you're in the elevator, you are in a non-inertial reference frame. And we've already seen you do not want to adopt perspectives from non-inertial reference frames. Next, you should only include forces acting on the woman. Forces by her don't affect her motion, and so this force, which is a force by her on the floor of the elevator, shouldn't appear on her free body diagram. It would go on the free body diagram of the elevator. Also, the cable is not touching the woman, and so it can't exert a force on her. You may be thinking, surely she wouldn't be accelerating up if not for a force by the cable, and that's true. But that force isn't on her, it's on the elevator. It affects how large the force is by the floor on her, but it is still the force on the floor which will affect her. And so the answer is B. There are only two forces on her, the long-range gravitational force, and the only thing she's touching is the floor, and so that's the only contact force that can act on her. So here's a book on a table, and the table pushes up on the book, and the book pushes down on the table. If I try and get the table to support the book by pulling, like by taking the book and putting it on the bottom surface of the table won't do a very good job of supporting the book, will it? These forces can be perpendicular to the surface. It is in this case, but how do we know? We know there's a downward gravitational force on the book, and it's in equilibrium, and so the vector sum of forces has to be zero. The only way that the vector sum can be zero is if the force due to the table is straight up, and that is perpendicular to the surface of the table. But what about a situation like this, where there's a block on a sloped surface? Now, the block isn't going anywhere, and so again, the only way for the vector sum of forces to be zero is if the force exerted by the slope is straight up. And notice that that's not perpendicular to the slope anymore. The dotted line is perpendicular to the slope, and the force that the slope is exerting isn't pointing in that direction. So the forces that surfaces exert can be at different angles to the surface. Even though we know it's straight up, it can be useful to think of it as a piece that's perpendicular to the surface and another piece that's parallel to the surface. So I'll redraw it that way. Now, that piece that's parallel to the surface is a frictional force. In this case, we would call it a static friction. Static just means nothing's moving, and nothing is moving here, and so that's why we call it a static friction. In particular, it's that the block is not slipping on the slope, and that's what tells us that this is a static friction. That other force I'm going to call a perpendicular force because it is perpendicular to the surface that exerts it. I'll warn you though, this is not the usual name for this force, but the usual name for the force causes enormous confusion for students, and so I'm not even going to tell you what that name is for now. Let's look a little bit more at how to decide whether an object has a static or a kinetic friction acting on it. And if you've taken physics before, you might have been taught that kinetic friction acts on things that are moving and static friction acts on things that are stationary. Unfortunately, that's entirely wrong, and you should forget you ever heard this if it's what you've been taught. Static friction acts between surfaces that are not slipping on each other, and kinetic friction acts between surfaces that are slipping on each other. You might not see the distinction, so let me show you an example. Suppose you are standing and you start to walk. So to start to walk, you need to accelerate forward. And your foot, if you're doing this normally on the ground, won't slip. And so the friction force acting on you will be a static friction. You're not slipping, but you are moving. even though you're not slipping. So you have a static friction even though you're moving. On the other hand, if you're on ice and you try this, likely your foot will slip. And so even at the start, when you haven't started moving yet, there's likely to be a kinetic friction force acting on you. What's really tricky about friction is figuring out which way it acts. If you've taken physics before, you might have been taught that friction opposes motion, but that's entirely wrong. Friction opposes slipping, and often that means it can act in the direction of motion. Let's keep thinking about you getting going while walking. So there's certainly a gravitational force due to the earth and a perpendicular force due to the ground acting on you. And to get going, you have to accelerate forward. The only force that can do that is the static friction acting on you due to the ground, and so the static friction force acting on you has to be forward, in other words, in the direction of motion. How does that happen? You push back on the ground and exert a static friction back on it, and the ground pushes forward on you. This is something I mentioned in the first lecture of this unit. It's an interaction pair, two forces that act in exactly opposite directions and have exactly the same magnitude. In this case, you on the ground and the ground on you. A general rule for how to figure out which direction a friction force points is that static friction acts to prevent slipping. So in this case, if there had been no friction, your foot would have slipped backwards. And so the static friction acts forwards to prevent that. Kinetic friction acts in a direction to reduce slipping. Or to put it another way, it acts to reduce the relative speed of the two surfaces that are slipping across each other. If you're getting the impression that friction is tricky, you're right. Friction is the trickiest force you're going to encounter. So let's practice. Let's think about a box that's being carried uphill by a conveyor belt. So it's going up the slope, and the belt is speeding up. And let's say the box does not slip on the belt. So which of these free body diagrams is the most correct free body diagram for this box?